Hi, my name is Evgeny. We will continue studying the Heta components. Today we will talk about compartments, species, and reactions. These components are used to describe the dynamics of molecules or other particles in volumes. The biological meaning of the terms is quite easy. Look at any biological model and you'll see different volumes and molecules inside them. They can move from one volume to another or transform into other molecules. So the volumes are compartments and the molecules here are species. Sometimes a model includes not only the molecules, but also the cells or other structures dissolved in the volumes. They can also be called species. When one molecule is transformed into another one, disappears or moves to another compartment, this is the reaction. It's important to mention about the inconsistency of the usage term compartment in systems biology and pharmacometrics. When we work with pharmacokinetic model, the compartment usually means the dynamic value characterizing drug concentration or metabolite. In Heta, the compartment term means the volume. In Heta, compartment, species, and reaction are classes that describe the corresponding biological terms. All these classes inherit from the record class, so you can use them as a regular record with additional properties. These properties simplify working with concentrations and provide correct transformation to ODE and other modeling formats. Let's look at them. The compartment is a specific class describing volume sizes. It doesn't have any additional properties, and it is used to clarify that some species can be located inside it. It's expected that the value of the compartment is expressed in units of volume or surface area or similar. Compartments are still records, so you can use any assignment scopes to describe its changes. As you see here, a compartment can be initialized by the initial value or expression, or can be a rule depending on other records. You can also write the process which changes the compartment value. The compartment can also be a dynamic value. Species have additional properties. First, all species must be referred to the compartment. We set the reference in the compartment property. The compartment with the corresponding ID should exist in the platform. The species describes the concentration of molecules at default. In other words, the units should be millimole per liter or nanogram per milliliter or something like that. For some reason, it might be more convenient to work with amount values instead of concentrations. Here, you should set isAmount property as true. In that case, the units should be in terms of moles or nanograms or something like that. Again, species are still the records, so you can use it as a dynamic value or static value or rule. The reaction is a class directly inherited from process. The main difference from process is that all the actors of reaction must be referenced to species, but not to any record. It's important to mention that the value of the reaction should always describe the rate in terms of amount per time units. For example, nanomole per second. Reaction class has the additional modifiers property, which is an array of references to species. Actually, the property is used rarely, but it was introduced just to support SBML compatibility. Let's look at how it works on a simple example with many compartments. This is a simple example to practice writing model with multiple compartments. There are 3 compartments and 4 species. One of the species, A2, is in the terms of amount, whereas the rest are in concentration terms. Let's start. As usual, I create an empty directory and drag and drop this to the VS Code icon. Then we are creating index Heta file. Then we are describing what we see on the scheme. The first compartment comp1 equal to 1. The species C1 describes molecules with an initial concentration equal to 10. Next step. The comp2 compartment is assigned by 2. There are two molecules there, C2 and A2. The first one is described by the concentration, equal to 0 at the initial time. And the second one is the amount with the initial value of 0. The last compartment, comp3, has a volume equal to 3 at 0 time. Molecule C3 inside the compartment is equal to 0 at the initial time. We have also three reactions here. The first one is the transport from comp1 to comp2. The second transforms C2 to A2 and C3. And the third one destroys C3. We should also clarify the values of constants. Before we simulate the model, I want to show you the ODE which describes the model. As you see, there are four dynamic variables. The left part of ODEs also includes the compartment values if we described concentrations. This is the main difference between dynamic concentrations and dynamic records. I want to simulate the model in MATLAB. So I am writing export action and setting format as MATLAB and file path model. As usual, let's open the console and print Heta build. No errors here. Open the model in MATLAB and run it. I want to plot only species C1, C2, C3 and A2. And now, to get more practice, let's see the examples which help us avoiding common mistakes. The first one. Someone included the species S1 and clarified the compartment comp1, which is constant. The problems here is the compartment must be of compartment class, not constant. The correct code is on the right side. The next example shows us that the compartment property must always be set, even if the compartment volume is not used directly. The next code is about the rules for reactions. The problem of this code is that the actors inside the reaction must be species only. If we want to include the dynamic volume comp1, we should use process class instead of reaction. That's all for today. Thank you for watching and subscribe to the channel. Bye.